Okay, so we've looked at the most common, the most popular, I should say, amplifier setup using a single BJT, which is that common emitter amplifier. And the common emitter amplifier tends to be the simplest circuit that has, relatively decent features as far as the input impedance, output impedance, and the gain that you can get from a common emitter amplifier. And it's a fairly simple circuit, and that's why it gets used the most. But as you saw from the solution, we reduce it down to a generic amplifier model consisting of 3 parameters: the gain of the amplifier, the input impedance, and the output impedance. And typically those 3 things are really all that we care about. So as long as the circuit is functioning within the input and output voltages, the generic amplifier model does an awesome job of reducing the circuit down to something very manageable, and that's exactly what we'll be doing in lab. Okay, now kind of carrying on with this idea of our amplifier, we can also, and there are reasons and benefits why you would do this, is to set up a multiple stage amplifier. There are different types of amplifier circuits, and each one of them has pros and cons to them. And so cascading these amplifier stages is a very powerful and very commonly done thing. So let's go ahead and let's just, since we know the common emitter amplifier, let's go ahead and cascade 2 common emitter amplifiers. So I would have some input signal that's coming in here, and first thing we would do is feed it through a bypass cap to get rid of that DC offset. We then go into our voltage divider bias for the first stage of our amplifier. That then feeds into the base of a BJT. We then have the same arrangement that we've already, covered and learned about. And from this point between the collector resistor and the collector of our BJT is where the output is taken from for a common emitter amplifier. We feed that through another decoupling cap in order to get rid of any DC offset that we had to have for the sake of this transistor operating within its linear region. And then we feed that into the next stage of our amplifier. And with that, we would go into, again, the base of our transistor while still having our voltage divider bias. And again, take the output signal from between the collector resistor and the collector of our BJT. And then that, again, we would decouple it so that we lose that DC offset. And from here, we take our V out. Of course, this is going to need some power to run all this, VCC. And we have our V in over here. And we set up a multi-stage amplifier as such. Now, when you go through the analysis process, the AC analysis process for each one of these stages, each one of those would occur independently. So we can take this first stage, reduce it down in terms of input impedance, output impedance, and gain. Same thing for this. So we get 2 sets of amplifier parameters, and we can go ahead and model this behavior very simply and straightforward using our generic amplifier model. Since we have two common emitter amplifiers, we get two generic amplifier models. Each one of them having an input impedance, as I'm drawing. And let's go ahead. We would label this as Zin 1, and this one would be Zin 2. And we can break this down into our source, load, and amplifier stages. Where our source, whatever our input is being taken from, whether this is a microphone, whether this is a small signal coming off of maybe a CD in the case of audio, and then you go ahead and need to amplify that, or this comes from some transducer, some sensor that you would use in an embedded system project, and then your load would be whatever it is that you're trying to drive. Maybe the load is a speaker, or maybe the load is simply the input into a microcontroller system, like an analog digital converter, which we will talk about later. Not later today, but in another class here very soon. And our source, we would model that as an AC source with some AC voltage and some output impedance. And as I mentioned previously, we always have to live with this. We always have an output impedance. Even if if I just have a sensor and it doesn't tell me anything, I have an output impedance. I just have to live with that. I'm always going to have this output impedance. Similarly, anything that I'm driving always has an input impedance. These are just facts of life that we have to deal with, and they can make or break our signal depending on the value that they have. You always want to feed a high impedance input with a low impedance output. That's my golden rule of connecting signals. You can look at everything you ever connect as being an output or an input. And we want our inputs to be high impedance and we want our outputs to be low impedance. As long as we have that situation set up, we are in a good position to not disturb our signals. Okay, we don't want to go and start losing half of our signal just because we connected, a medium impedance to a medium impedance. So if you're looking at the output of something, desirable would be low impedance. And if you're looking at the input to something, what's desirable is high input impedance. Okay. Now, each one of these amplifier stages has some gain associated with it. And an output impedance. So we have a Z out 1 and we have a Z out 2, and our input to, say, our first stage is a V in that is created from the voltage divider that's created by the impedances, and that will get multiplied by the gain. So this is AV1 for our voltage gain of our first stage times this V in as influenced by these two impedances. So V in. Okay. Same thing again happens. Our output voltage here gets affected by these two impedances. So we have a gain multiplied by our input voltage, but of course now these two impedances have created a voltage divider again, so you would take this value, multiply it by Zn2, and divide that by both Zout1 and Zin2. And then you get a Vn2. Okay, and then we have a gain associated with the second stage. So we have an AV2 times Vin2, which produces a voltage, and then that again gets influenced by these two impedances. So we get finally a V out across our load. Okay. So we can definitely cascade these amplifiers, but note now we have a Vin influenced by these two impedances. We have a Vin2, which again is influenced by these two impedances. And we have a third point here where our final output voltage is affected by these two impedances. So 3 places where the impedance has an ability to mess with us. Okay, and we can go ahead and solve these voltages. Let me switch colors because everything here is in black. Let's go to red. Okay, so Vin, what did I call this? I labeled this as Vin. Oh, let me make this Vin1. I'll change that over here as well, Vin1. Okay, so Vin1 is simply going to be equal to, well, the voltage that's being applied to the two impedances that are acting as a voltage divider, so Vs, and now just apply our voltage divider equation, so Vs times our R2, which is Zn1, all divided by Zs plus Zn1. Okay, that takes care of solving for our first voltage. Then, to solve for Vn2, Vn2 is going to be equal to, well, the gain of our first stage times the voltage as influenced by our impedances. So AV1 times Vn1 times our R2 of our voltage divider, which is Zn2, all divided by Zout1 plus Zn2. Okay, so just the voltage divider equation with the voltage that's being created or produced by our first stage multiplied by the voltage divider of our impedances. Okay, so that takes care of Vin2. Now to solve for our final voltage, V out, so that we know exactly what is being applied to this load, V out is going to be equal to, well, AV2 times Vin2 times ZL divided by Zout2 plus ZL. Okay? So pretty straightforward once you're comfortable with that voltage divider equation and the idea behind these generic amplifier models. They just do a much, they make it much easier for us to understand what's happening to the signal as it goes through the two stages without having to concern ourselves with the biasing point of this, the load line, and all of that. Once we've designed our common emitter amplifier to do what we wanted it to do, going through here to see how the signal is affected is very straightforward, hopefully, at least. Okay, now as I alluded to, there are different types of amplifiers, and each one of them has a pro and a con. Now, this isn't a class that is spending the entire class on all of these different amplifiers, and believe me, they would fill up a class, if not an encyclopedia. But let's go ahead and at least cover some rules of thumb and some general conceptual ideas, and we'll see one more type of amplifier, but I will just be giving the equations for that. So, first off, a couple of things here. This I'm going to refer to as the golden rule of signals. Normally, I would call something like this a rule of thumb. However, this is bigger than a rule of thumb. This is crucial. Always drive, let me put this in red. Always, 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 always. This rule never gets broken. Always drive a high impedance input with a low impedance output. Okay. If you follow this, anytime things are not making sense, anytime your results are not adding up to what you expect, I get students that get into 346, 347, 447, they're working on a project, they're connecting something, and they come to me, then they're like, hey, I calculated that it should be this value, but I'm actually getting this. And I look at it, and the first thing I ask is, I'm like, impedances? And they go, huh? And I'm like, impedances. And then they go ahead and I draw it out as one of these generic amplifier setups, just like we did earlier. And all of a sudden they go, oh. And then I tell them how to fix it. And all of a sudden they go home, they fix it, they come back, they're like, it worked. I'm like, yes. I'm like, because this is always true. We have to live with this. Okay. But high impedance, low impedance are pretty generic. What does that even mean? Okay, now we get to a rule of thumb. What is high? What is low? Now, high impedance is, well, it's going to be, it's always relative, you know. The high impedance is relative to the low impedance. The low impedance is relative to the high impedance. But generally speaking, low Z we would consider to be, less than 150 ohms. Okay, 50 ohms, 100 ohms, even 200 ohms. Low-ish impedance, okay? Now, I'll also say medium impedance is going to be somewhere around 5K. And high impedance, man, I just wish that this could be, I wish I could have infinite ohms for my high impedance all the time. I can't. But 10K can be high impedance. So can 1 mega ohm, all the way up to 10 mega ohms. Okay. If you think about probably, let me look at my oscilloscope over here. My oscilloscope is 1 mega ohm input impedance. Okay. That's my oscilloscope. That's a piece of precision test equipment that's being used to display waveforms, and I hook this up to my circuit. I'll just call it a DUT, a device under test. And I go ahead and I hook up my probe of my oscilloscope here, and let's connect to the ground somewhere over here. You know, the whole point of me hooking up this oscilloscope, it would not do me any good if hooking up this oscilloscope affects my signal. If my oscilloscope acted like a low impedance, it's going to start drawing a lot of current, which will affect my signal. We've seen that when you hook up amplifiers to each other, when you hook them up to a load, and when you have a source hooked up to the input of something. So ideally, I would love for my oscilloscope to be infinite ohms of impedance, because if I had infinite ohms of impedance, if I had, oh, I drew this backwards. If I had infinite ohms of impedance, I could hook up this oscilloscope probe to anything and be guaranteed that I would never affect a signal, meaning that my displayed waveform would be a perfect ideal representation of what's going on in this circuit. But unfortunately, I can't measure or look at a signal without affecting it, because I have to connect something to look at that signal, and by doing that, this wire has some impedance, and this input is an amplifier which has some type of impedance, so I have to live with this situation. So you do the best that you can, and you just try to make it a very high resistance. I can't make it infinite, but I can make it sufficiently high such that its influence is negligible. And that's exactly what they've done. Well, that value ends up being 1 mega ohms, is pretty high. That's sufficiently high in order to not disturb my circuit under test over here. Okay, but depending on what the impedance is on the output of that signal, I can get away with smaller and lower values depending on what that output impedance is. So, you know, if I had 50 ohms or 10 ohms of output impedance, 10K would be considered high. But if I have, you know, medium impedance of 5K, well, then now I really need to get quite a bit higher than 5K, and 1 mega ohm is pretty high for impedance. So these are just some rules of thumb to keep in mind as far as gauging what's considered high impedance, what's considered low impedance. Okay, so let's talk about some features of our common emitter amplifier. Okay, as it turns out, the input is actually medium impedance. Generally speaking, it is hard to create a common emitter amplifier that has a very high impedance. Okay, that's one of the drawbacks of a common emitter amplifier. It's the most useful of our amplifiers, but we generally have a medium input impedance. And it's kind of hard to design common emitter amplifiers that have very large input impedances, like 100K. That's very difficult to get out of a common emitter amplifier. Okay, but what about the output? Well, the output ends up also being medium impedance. And in fact, it ends up being generally a little bit higher, 5K. Well, again, this is not ideal. I would like for this to be low impedance, and I would like the input to be high impedance as to not disturb my signals. Okay, these are probably the two most important features that I'd say about a common emitter amplifier, but there's also (180-degree) phase shift between the input and output. And what I mean by that is our signal gets inverted. And we saw this when you just look at how it's connected, because you're taking that output signal from the top of the collector. Your input, when it goes high, your output goes low. So you do get an amplification. You get a larger output than you have of an input. However, it is flipped. It's inverted. It's 180 degrees phase shifted. The output is relative to the input. Now, generally speaking, this isn't that big of an issue, but it could be depending on your situation. If you're talking about an audio wave, an audio signal, who cares if it's inverted, right? Your ears aren't going to notice the difference between 180 degrees phase shifted audio versus, non-inverted. But if it's not audio, maybe if it's a temperature sensor, yeah, you need to be concerned about this. And so in software, you might want to go ahead and flip it back, or you have 2 stages where each stage does an 180-degree phase shift, and as long as you have an even number of stages, you get your original non-inverted signal. But just important to keep in mind that your common emitter amplifier does that and has these generalized impedances on the input and output. Okay, and I should also say the input is on the base, and the output is from the collector. Now, this is the only amplifier we've looked at with a BJT, so probably the question that's popping up now is, well, what's not having the input on the base? What's not taking the output from the collector? There are plenty of amplifiers that do not have their input on the base, output from the collector. Okay, so this is kind of, now that we should be very comfortable with the common emitter amplifier, is there another type of amplifier that could help us out of this situation? Yes. And that's going to be the common collector amplifier. Let me do this on another sheet of paper. Okay, the common collector amp. Well, let me go ahead and list the features for this one first. Now this is kind of nice. The input is still on the base, but the output is taken from the emitter. So instead of taking it from the collector, as we did for the common emitter, for the common collector, the output's actually taken from the emitter. Now, here's one problem with the common collector amp. You get no voltage gain from it. So we can say always has a voltage gain. Of 1. Okay, now that seems like, what good is an amplifier that doesn't amplify? Well, it does amplify. It just doesn't amplify voltage. It amplifies current. And that is implied in these next two features. Input can be very high and the output is relatively low. Okay, so the common collector amp does give us this very desirable feature of having a very high input impedance while having a low output impedance. Now, if you think about what's required in order to do that, so even though we only have a gain of 1, I am taking in very little current. Let's just say less than 1 milliamp. But I am able to source 50 milliamps or 10 milliamps, much more than I can on the input. So for the usefulness of not affecting our source, but being able to drive something with a lower impedance on the load, this is great. Our input is very high impedance, our output is very low impedance, but we have a voltage gain of 1. So this amplifier is more of a current amplifier than it is a voltage amplifier. Our common emitter amplifier gives us a good ability to adjust the voltage gain, but it doesn't do a good job as far as the current is concerned. But that's why I showed how you can cascade amplifiers, because you can put a common collector amplifier in front of a common emitter amplifier. You can get your voltage gain from this amp while you get the high input impedance of our common collector amp. Now let's go ahead and let's just look at the circuit. We're going to have our input, we're going to do the same thing. We're going to use a voltage divider bias, and we're going to feed that into our BJT, the base. Notice that the collector is now completely straight tied to VCC. We don't have a collector resistor up here. We will have an emitter resistor down here, and the output is actually taken from the emitter down here. Now, if you look at the common emitter amplifier, we're taking the output from here, and we have that resistor up here. And that's where you actually get the voltage gain from, because the current is increasing through the collector current is increasing, and so you get the output taken as that voltage drop across VCE and the emitter resistor. But when you look at a common collector amplifier, you're actually taking the output from down here. So you don't get any voltage gain, but you do get current gain. And RE is here just to limit the current from the collector to the emitter so that we don't damage our transistor over here. But you can get a lot more current from this guy, hence why we can get a much lower output impedance from this. Okay, now you can solve this using the same exact technique from previously. The previous two classes covered how to calculate that common emitter amplifier and go through the AC analysis using the T equivalent model to represent the BJT, and you can solve for that. And absolutely, you can do the same exact thing for this, and you're going to see that your AC model ends up changing a little bit. We don't have time to actually go through the entire AC analysis portion. As you saw, it kind of took quite a while for the common emitter amplifier, but I will give you what the results are. Okay, so RZ in equals R1 in parallel with R2 in parallel with beta plus 1 times our dynamic emitter resistance plus the emitter resistor. Okay, that's our Z in. Our Z out is going to be the emitter resistor in parallel with the dynamic emitter resistance. AV, the voltage gain, I already told you, is 1. However, when you go ahead and solve it using the whole AC analysis procedure, you're going to find that the voltage gain is equal to the emitter resistance divided by the dynamic emitter resistance plus the emitter resistance. However, because our dynamic emitter resistance is much smaller than RE, you can consider its effects to be fairly negligible as far as this equation is concerned, compared to RE. RE should be orders of magnitude much larger than RE prime, and so you end up getting RE divided by RE, which ends up being 1. And we are going to have one more thing in here. We do have gain, but that gain comes in the form of current gain, and the current gain ends up being approximately equal to minus beta. So we can generally get about 100 times more current coming out of this than we have going into it. You can't say the same about the common emitter amplifier. So this amplifier is a very useful one just for the case of solving the issue of high impedance being driven by low impedance. When you want to cause that situation to occur, this common collector amplifier is going to be your friend. And as I said, these are the features that we get out of a common collector amplifier. Okay, so let's go ahead and let's stop that there. And let's jump over to lab. Let me pull up the lab. Okay, here we are. Let me kind of go over what we're going to end up doing in the lab. So 311. Okay, now I'm calling this Lab 5, the BJT Common Emitter Amplifier. This is a new document that is up here compared to what we had before. So if you did previously download this, make sure to download the new version as the circuit's changed quite a bit. Okay, so we're going to have essentially three large steps with this lab. The first one is going to be calculating this by hand. Okay, so before we even touch LT Spice and simulate this, I want everyone to step through that process of the AC analysis. Now, let me go ahead and give you a word of caution here. This circuit is a little different than what was in lecture. There's a change over here. We actually have a new resistor that's been added to the emitter of the BJT. Now, why would you do something like this? Well, this ends up being useful as far as being able to control the parameters of your amplifier and being able to change more easily how it behaves in DC versus AC. And the reason here is because this C2 capacitor ends up acting as a short as far as the AC signal is concerned. Because this cap is acting like a short, it allows R5 to disappear for the sake of doing the AC calculations. But the 5.6K matters when it comes to the DC portion. So as far as being able to control your biasing point as well as your voltage gain, this arrangement gives you a bit more flexibility as far as implementing a practical circuit that does its intended job. Okay, but it does change your AC analysis. So you will have to step through that entire process from the previous two lectures. You won't be able to simply apply the equations and get the correct answer. You will have to draw out the AC analysis and reduce that circuit to find out what the new equations are that are applicable to this circuit. Okay, now I'll go ahead and give you some foreshadowing. There are three ways to modify this circuit that changes the equations. It's not just adding this resistor over here that doesn't have a cap across it. This is only one way. There is another way. That other way is going to pop up on the exam. So there are three different types of common emitter amplifiers that you can come across. Each one, when you step through the AC analysis, yields different equations. So we saw one in lecture. We're going to have another one in lab. And then the third one is going to be on the exam. So a little bit of foreshadowing. Could you go ahead and search online for those other versions? Sure. But I just wanted to give some motivation that just applying the equations that I derived is not good enough. You will have to do and perform the AC analysis on the next exam. Well, actually, that would be the final exam. Okay. So you will go through the DC analysis, the load line, the AC analysis. You'll derive your amplifier parameters. And then you will apply those amplifier parameters to two different cases. And this does walk you through that. So you're going to do one case where you have the load resistance set up to be relatively high. Now that's going to be desirable. That's going to not affect your output signal very much. And then you will also do the same thing, but with a much lower load resistance. So over here, you will be seeing that your output signal is going to get disturbed significantly. Okay, so you're going to calculate all of this by hand first. Then we're going to go ahead and simulate it in LT-SPICE. When you do that, you're going to verify that your hand calculations are relatively accurate. Okay, now LT-SPICE is capable of modeling this circuit to a higher degree of precision than we are. It's more capable of doing that than I am. Just because it's taking into account a lot more than we are. When we learn how to solve these circuits, we're solving them. We are doing approximations, right? We didn't fully solve the DC analysis portion. The AC analysis portion, we're using a T equivalent model with a dynamic emitter resistance. How accurate is that? It's accurate enough, but it's not as pinpoint world accurate as LT-SPICE can get. Okay, so I tend to find when I am working in this analog domain supporting digital circuitry for the sake of embedded systems and FPGAs, the approximation techniques get you 90% of the way there. LT-SPICE and circuit modeling gets you the next 5-6% of the way to your completed goal. And then only by actually creating it and testing it and subjecting it to real world influences like electromagnetic radiation and other things that are going on that LT-SPICE isn't capable of simulating, then you get to that last 99-100%. But the approximation techniques that we learn get us almost all the way there. Circuit modeling makes up the remainder. And then once you've done the simulation and verified the hand calculations, then you'll get into doing the breadboard prototype. Now for the breadboard prototype, you're going to have to construct the circuit and then we will be applying the test input from the MyDAC, and we will be receiving the amplified output back from the amplifier through the input, the oscilloscope input to the NI MyDAC. And like I said, I do have all the materials put together, and I will be putting together a walkthrough video on how to connect this up, what these signals are, and all of that. So don't worry about that. It actually is pretty straightforward once you get the software installed. This guy just comes up and works pretty well. So I think it's going to work out really great for this class. Unfortunately, we got it this late in the game, and I had no control over that. But at least we have it now. Okay, one thing I did want to note was supplies for this class. Okay, so actually I have the same circuit set up over here. I will mention when I'm breadboarding, I try to use the least number of wires as possible, and I try to make my circuit look like the actual circuit. And so I find that with a little bit of creativity, you can minimize the use of these wires. These wires are prone to breaking, so you can have less issues with your circuit if you try to use a least number of wires. And then I try to make my circuit look like the circuit from the schematic as much as possible to make probing it and looking at it and identifying the components just so much easier. Okay. Now you can take this to a higher degree of breadboarding cleanliness where you shorten up all the legs and you make it all low profile to the board and everything's just beautiful and neat and organized and right angled lines. The reason I tend to not do that is because I want to reuse my components as much as possible, so I don't like to cut them and make them all short and as clean as they could be, unless it's a very sensitive circuit that the breadboard's working against me because these pins, these point contacts have a little bit of inductance and capacitance and resistance and all sorts of unwanted parasitic parameters. But if I'm at that level of where my circuit doesn't work because of the breadboard, then I'm going to be soldering it. So, you know, that's my trade-off. I like to leave my legs, my leads and legs of my components intact so I can reuse my components. Now, as far as the values are concerned, you will need a 2N3904 resistor, BJT transistor. You will need 3.K 470 ohms, 5.6K 47K ohm resistors. Hopefully you have all of those in your resistor component pack. So if you buy a kit of assorted resistors, you should have values that are pretty close to those. They should be the same. These are standard values that I picked. So these should exist in most assorted resistor kits that you would get. So I'm not expecting too much difficulty with sourcing the resistors. This is about the most common transistor on the face of the planet. 2N3904s are everywhere. The 15 volts comes from the MyDAC, so we shouldn't have an issue with the applied voltage here, the voltage up here. We shouldn't have an issue with our resistors or our transistors. And the capacitors, I chose to all be the same value, 1 microfarad. And so we shouldn't have an issue getting those values either. I updated my website as far as sources for those components. So let me pull that up. So as far as supplies, parts, tools, etc., let me go ahead and mention there's a store over in Westminster called JK Electronics. They're kind of the last electronics store that we have. Radio Shack doesn't exist anymore, at least not. I haven't seen one around here. I think they still do exist. There's a Radio Shack somewhere, probably in some little town in the middle of nowhere. But JK Electronics is a legit electronics store where you can buy all of all of the components. So here's the trade-off. When you buy on Amazon, yeah, it's cheap. You can get things, but you typically pay $10-12 for a bunch of components, and you only need one of them, but you need another one that comes in another Amazon purchase, which is another $10. So now you're looking at $20 just to get 2 little items, whereas JK Electronics, you can go in there and you can purchase 1 resistor if you want. You can purchase 1 transistor if you want. Okay. Now that being said, I think resistor assortment, everyone is going to need one of these somewhere along the lines. And so I put 2 different kits listed. And I'll just quickly go over these. 56 different values, 20 pieces each, $10. This is really all you would need for a very, very, very long time. What I actually do is I keep my resistors organized in a box. This is my non-standard resistor box. I keep them all in here and labeled, and then I buy these giant packs and I refill this as I need them. But one of these is all you need. And then there's also, if you want the nice bagged route, the same thing over here. Actually, this has 100 different values. This one's kind of expensive, $27 for a bunch of resistors. Here, the 50 different values for $15, and these all come in plastic baggies as well. So yeah, if you pay a little more for convenience. Okay. Oh, and apparently it also comes with a couple of extra adjustable trimmer pots. That's cute. Okay. So that's for resistors. For capacitors, again, I updated this section on the website. There are electrolytic capacitors and ceramic capacitors, two fundamental different types of capacitors. Now, the benefit is electrolytics can go much larger in the number of farads. They go into the micro and millifarad range, where ceramics tend to be in the pico farad and nanofarad range. However, as of let's say early 2000s, a process came out for manufacturing ceramic capacitors called multi-layered ceramics. And now, very cheaply and affordably, you can actually get ceramic capacitors that go into the lower end of that microfarad range. And that's actually my first link over here, ceramic capacitor kit. And again, you probably would not need much more. This has 1 microfarad, which is what I used in the lab, and it goes all the way up to 10 microfarads. Now, here's the drawback with this parts kit, which is there's nothing above 10 microfarad and there's nothing below 0.1 microfarad. So generally speaking, your smaller values like 10 nanofarad and the picofarad range, you'd have to get other ceramic caps. And if you wanted to go above 10 microfarad, you'd have to go with electrolytic caps. I don't know. It's hard. I would much prefer if I could assemble a kit for this class and just put 2 or 3 capacitors in a baggie and, sell them for a couple of bucks to all of you guys. But I don't want to handle money and exchanging stuff like that with students. But that being said, this is actually pretty decent. You could always, buy one of, if you really wanted to go low cost and get all of your options, I would buy a small valued ceramic kit. I'd buy one of these and an electrolytic kit, and then I'd split it like 4 ways with 4 other students or 3 other students, and then you'd be getting 10 of each value and be paying like a total of $10 for everything. But I will let you guys decide how you want to do that, or you go to JK Electronics and you can purchase low value single onesie twosies of components over there. There's also things that I have found in here. I have seen some kits on Amazon. Kits like this that have LEDs, resistors, electrolytics, ceramics, and some common diodes. Does this have a transistor? I think it does. 2N3904 is in this, and it comes with some resistors and electrolytics. Here's the problem with these things is 1 month one vendor is selling one thing and another month another vendor is selling another thing. I don't have the time or desire to be constantly watching on Amazon what's available and what's the best bargain. Like, that's just way too much work. Every semester there's different vendors selling different things, and sometimes they're out and sometimes they have them. They sell assorted capacitor resistor kits at JK. They do. They have them somewhere in their aisles. I've seen them. But they're not going to be the same bargain as you would get on Amazon for those resistor and capacitor kits. But they do have them at JK. JK is one of those stores I can just go to and like hang out there for a couple of hours, just meandering the aisles. And then when I go at checkout, I end up like, why am I spending $200? Because I'm a dork. Because I'm a nerd. Okay. Let me go back over. Okay, so resistors and capacitors, I updated that on my website. And then there's other things I kind of addressed as well. And I try to create my website such that it's a good, valuable resource to get anyone started in our field and industry. So it's just kind of an evolving process. Okay. So I'm going to go ahead and stop the recording there. I wanted to record that part where I was looking over the component values and kind of showing links from the website and kind of talking about the components in general. Where do we get the 2N3904? Let me go ahead and stop my recording.